Equipment Lesson 4 covers focal spot and the anode heel effect. Two concepts that directly affect image sharpness and exposure uniformity across the field. We cover the line focus principle, actual versus effective focal spot, small versus large focal spot trade-offs, the geometric unsharpness formula, the anode heel effect with its clinical application, and focal spot quality control. 11 minutes. On this diagram you can see the geometry that defines the line focus principle. Electrons from the cathode strike the anode surface at an angle, typically 15 degrees in diagnostic tubes. The actual focal spot is the true electron impact area, a rectangle shaped by the focusing cup. The effective focal spot is what the image receptor actually sees when looking up at the anode from below. Because the anode surface is angled, the projection of the actual focal spot onto the plane of the image receptor is smaller than the actual area. The formula is effective focal spot equals actual focal spot times the sine of the anode angle. At a 15-degree angle, sine of 15 degrees equals approximately 0.26, the effective focal spot is only about 26% of the actual focal spot size. This is the engineering genius of the line focus principle. A large actual focal spot handles the heat load of the exposure. A small effective focal spot provides the resolution needed for diagnostic imaging, both at the same time. This dual bar chart shows resolution and heat capacity at 5 focal spot sizes from 0.1 mm through 2.0 mm. The green bars, resolution, decrease as focal spot size increases. A 0.1 mm focal spot resolves approximately 10 line pairs per millimeter. A 2.0 mm focal spot resolves only about 1.5 line pairs per millimeter. The orange bars, heat capacity, increase dramatically with focal spot size. A 2.0 mm focal spot can handle 20 times the heat load of a 0.1 mm focal spot. Clinical decision rule: use the smallest focal spot that the heat load allows for any given examination. Small focal spot. For extremities, magnification radiography, and mammography. Large focal spot for abdomen, thorax, fluoroscopy, and any HIMA-S technique where heat load exceeds what the small focal spot can handle. The goal is always the best possible resolution that the technical requirements of the exam allow. The anode heel effect is one of the most clinically useful physics concepts in radiography. And it is directly tested. Geometric unsharpness, also called penumbra, is the blurred edge around a structure caused by focal spot size. The formula, UG equals OID divided by SOD, times focal spot size, where OID is object to image distance and SOD is source to object distance. Three factors control penumbra. Focal spot size: larger focal spot equals more penumbra equals more blur. Minimize by using the smallest focal spot that handles the heat load. OID: larger OID equals more penumbra. Minimize by keeping anatomy as close to the image receptor as possible. And SID: longer SID equals less penumbra. Use standard 40-inch or 72-inch SID. Magnification radiography intentionally increases OID to produce a magnified image, but this worsens penumbra. Using a small focal spot is mandatory in magnification radiography to keep blur diagnostically acceptable. 5 focal spot QC methods tested on the registry. The star pattern test: radiograph a star pattern resolution. Target blurring of the spokes indicates the effective focal Spot size. Most commonly used clinical method. The pinhole camera, a tiny hole in a lead disc placed over the tube port, produces an image of the actual focal spot. Shape and size. Precise but complex setup. The slit camera, a narrow slit aperture radiographed in two orientations, measures focal spot dimensions in both axes independently. This is the NEMA standard measurement method. Bar pattern resolution, quick qualitative verification using lead bar patterns at known line pair values. Good for routine checks between detailed measurements. Acceptance criteria per NEMA. Focal spots up to 1.5 mm can be up to 50% larger than the nominal rated size. Focal spots above 1.5 mm can be up to 40% larger. Tested at installation and annually. 3 focal spot and heel effect questions. The answer is B, shoulders toward cathode side, lower chest toward anode side. The anode heel effect produces higher beam intensity on the cathode side, orienting the thicker shoulder region toward the cathode side produces more uniform exposure across the full chest. Image. Apply this principle whenever significant thickness gradient exists along the long axis of the field. The answer is B, the angled anode surface projects a smaller effective focal spot than the actual focal spot. The line focus principle describes how angling the anode target reduces the projected effective focal spot compared to the actual electron impact area. Formula, EFS equals AFS times sine of the angle. At 15 degrees, effective focal spot is approximately 26% of actual focal spot size. The answer is B, small focal spot, to minimize geometric unsharpness that worsens with increased OID magnification. Radiography intentionally increases OID, which worsens penumbra proportionally. You covered the line focus principle diagram with the actual versus effective focal spot geometry, the resolution versus heat capacity chart, the anode heel effect with its color gradient intensity visualization, and clinical rules, geometric unsharpness, and the penumbra formula, and all 5 focal spot QC methods. These are precision concepts, apply them every time you position and select technique.